In Euclidean and Minkowski spacetime, straight lines are characterized by two main properties. The first property is that if we consider 2 points P and Q, and we consider all the curves that join these 2 points, a straight line is the one along which the distance between the 2 points is shortest. Okay, so the extremise distance. The other property is that they are autoparallel. Okay, and this autoparallel is what we mean by straight also. This means that if you consider the vector's tangent to the straight line at any point, let's say the point P and the point Q, okay, and you parallel displace this vector here, well, you find that this vector is parallel to the other one. Here we are using the standard connection in flat spacetime, which in Cartesian coordinates has vanishing connection. Okay. There is another way of saying the same thing, which is that I can obtain the tangent vector at any other point by parallel displacing the tangent vector at a given point. Okay, so I parallel transport it to R, to Q, and to any other intermediate point. So we are now in some general geometric space in a differentiable manifold, and we want to generalize these two properties. In order to generalize this property, it's clear that we need a metric because we want to measure distances, but we don't need a connection because we haven't mentioned the parallel transport at all. If we want to generalize the second property, it's clear that we need a connection. Okay, but we don't need a metric because we are not, in order to say that two vectors are parallel, we don't need a metric, and we are not measuring anything. So we can generalize these two concepts independently. One, the first concept, can be generalized in a space which only has a metric and forgetting about a connection, and the other one in a space that has a connection and maybe not a metric. Well, it shouldn't be surprising that the two generalizations are not equivalent. They are equivalent in flat spacetime, in Euclidean or Minkowski spacetime, but they are not in a general spacetime. The two concepts, okay, that we obtain, which are in principle not equivalent, are the concept of geodesic. So, which is the concept that generalizes is the curve that extremizes the distance between 2 points, where the distance is given by a given metric now, and autoparallel curves. Geodesic curves and autoparallel curves. So the second would be curves whose tangent vectors can be obtained by parallel displacing the tangent vector at a given point along the curve. Then it shouldn't also be surprising that when we consider the Levi-Civita connection, which, remember, only depends on the metric, geodesics and autoparallel curves are exactly the same thing again. They are not in general, okay, for a general connection. We are going to study these two concepts because each of them illuminates a different aspect of these curves, which will be in the end geodesic and autoparallel, but the properties that they refer to are interesting separately. In all cases, the most important object that we will work with is the tangent vector to the curve. So we will have curves parameterized by some parameter lambda, and we will consider the tangent vector at a given point. Okay, so we evaluate this derivative at different values of lambda. In the Lorentzian case, which is the one that has to do with gravity and with physics in general, this vector will have some causal character. It can be null, time-like, or space-like. For a general curve, the causal character of the tangent vector can change along the curve. It doesn't really matter. You just can conceive and draw curves that have that property. But from the physical point of view, if this curve is going to be the wall line of a particle, it has to be, the tangent vector has to have a definite causal character all along the curve. So there will be curves whose tangent vector is time-like all along the curve, and this will be a time-like curve. And another possibility is that it is a null curve. So this corresponds to the wall line of massive particles, and it will correspond to the wall line of massless particles. Wall line of massless. Okay, then among these all these possible time-like curves, we want those that extremize the distance between 2 points, the geodesics, or those which are autoparallel, because the tangent vector is parallel to itself all along the curve. And the same for null curves. Okay, so these are the ones that can correspond to wall lines, and on top of this, for each of them we can select those which are geodesics or autoparallel curves, and then we will study what happens when the connection is just a little bit Civita connection, and we will see that all the geodesics are autoparallel and vice versa. So let's start with autoparallel curves. If you remember how we introduced parallel transport and the covariant derivative, we said that the covariant derivative could be used to compare the values of vector field at a given point, the value that one obtains at that point because of the definition of the vector field, because it assigns a vector at to any point, and the vector that one would obtain from another point by parallel transporting it to the given point that we were studying it. If the distance or the displacement between these 2 points is delta x mu, the condition that these two vectors are parallel was this. Okay, so we can say that in this case the vector is parallel to itself when we parallel transport it along this displacement. If it happens that the vector is covariantly constant, the vector field is covariantly constant, this is sometimes called as a parallel vector field. And it's parallel because now this expression will be 0 for any delta x mu. So this will happen, this property will take place in any direction. Okay, and observe that this property here is really invariant under general coordinate transformations, because we should take into account that this infinitesimal displacement can be replaced by a vector. Okay, now consider vectors tangent to some curve, okay, at different points. They are given by the derivative of the function that embeds the wall line in space-time. Now the idea is that if we want to compare vectors, this vector here, for instance, with the vector that we obtain by parallel transporting this one to the same origin, okay, we can use this concept here, and since the displacement really is another tangent vector, well, we can say that the vector will be parallel. This tangent vector will be parallel to itself at a different point. If this, which represents the difference between the parallel transported vector and the vector defined at that point, is either 0 or really proportional to the tangent vector itself with some proportionality constant f that can be that may depend on lambda, because it could be different at every point. Okay, when a curve x mu of lambda satisfies this condition for all values of lambda, we say that this is an autoparallel curve. Okay, so let me just go back again. This is the simplest possibility that we considered at the beginning, that this is 0, but if we think a bit harder, we realize that two vectors, when in order to be parallel, the difference doesn't have to be identically 0. It just has to be something proportional to the vector. Okay, so this is just realizing that we can be a bit more general. The other thing that we have done is to replace a vector field by a set of vectors which are defined only along the line, and the displacement by the tangent vector itself, because these displacements are also the tangent vectors. Okay, so this equation will have this form more explicitly. Remember that this is partial x nu of x dot mu plus gamma nu rho mu x dot rho equal to f x dot mu. This is the form of the equation, and it is not clear how to do this, but if we use the fact we use the chain rule and nothing else, this is just the derivative, another derivative with respect to lambda. So this first term is just x double dot mu. Here we have gamma nu rho mu, and we have x dot nu, because this is just x dot rho equal to f x dot mu. And this is the equation of the autoparallel curve. As you see, the metric is not involved at all in the equation, and the only thing that appears, the only element that gives you information about the space or the structure of the space, is the connection. And f can be anything. Okay. Now, an important observation is that this term in the right hand side can always be eliminated by reparameterizing the curve. So this means using a different parameter. So we are going to replace lambda by another parameter that we are going to call s, for reasons that will become apparent in a second. Okay, if we do this, then x dot, okay, or the original x dot that we were using here, which was the derivative with respect to lambda, will now be given by this using the chain rule. And now we are going to change the notation. We are going to denote with a dot the derivatives with respect to s from now on, okay, in this calculation. Okay, now we have a second derivative here, so we have to compute it. And this is the lambda of what we just computed. the first term will give us the second derivative of s with respect to lambda, x dot mu plus ds d lambda, and if we apply again the chain rule, we are going to get just another term, ds d lambda, and x double dot mu, where x double dot mu is now the second derivative of x mu with respect to s, not with respect to lambda. Okay, we have computed everything. We go to the autoparallel equation here, and we write d square s d lambda square x dot mu plus ds d lambda square x double dot mu plus gamma stays as it is because this is not a change of coordinates in space-time, is a change of parameterization. And okay, these were here in the original formula derivatives with respect to lambda, so now they give you these dots, x dots, with the new definition of x dot, and we also get a factor ds d lambda for each of them. And in the right hand side we get f, another factor ds d lambda, and the new x dot mu. So first of all we write this as we just take this term to the right hand side, okay, and in the right hand side we get minus common factor x dot mu minus d square s d lambda square x dot mu, and because I just put it in the right hand side, I get rid of all this. Okay, and I can always find the solution for this differential equation equal to 0. So under this assumption I can eliminate this factor ds d lambda squared, and the equation takes this form. And it is a form that you should remember from I think it was the second lecture where we introduced the proper acceleration, and it was defined in terms of proper time. Here we cannot talk about proper time because proper time was defined in terms of the interval. So this s, which has the property that the autoparallel equation is written like this and with vanishing right hand side, this is again the autoparallel equation, and s is the affine parameter. In this context, and this would be x mu of s would be an affinely parameterized autoparallel curve if it satisfies this equation. Now let us discuss the second kind of generalization. It was the first, the way in the order in which we introduced them. So this is the generalization of the curves which extremize the distance between any two given points. And okay, we have introduced a functional that gives you the distance between any two points in space-time. Okay, so if this is along some curve, okay, so let's say that this dependence is for some curve x of lambda. This is given by the integral between lambda 1 and lambda 2, and remember that this means that x of lambda 1 is x1 mu, and the same for 2 of different d lambda and the square root of g mu nu of x x dot mu, x dot nu, where these are just derivatives of x mu with respect to lambda. Okay, if we in the past we consider this functional only for the motion of massive particles, so the curves were always time-like, which meant that this was positive. If we wanted this to be more general and include also spatial distances, we would have to add a minus sign, because in that case this quantity here would be negative. So in general, so if we don't want to make any assumptions, you just write the absolute value and that's it. Okay, so this functional gives you the proper length of the curve between the points x1 and x2. We showed that when we studied because the action for a massive particle, that this functional is invariant under parameterization. So if we change lambda by another parameter, lambda prime, then we change everything accordingly, the distance, this proper distance, remains the same. When so I'm not going to prove that again. Let me just remind you that this proper length for time-like curves would be proper time. Okay. So this would be a proper time when the curve is time-like and can describe the motion of a time-like particle. This S between x1 and x2 then will be given by c times tau. This I am knowledge that I am a bit sleepy when sloppy sorry, when I talk about the proper time. Sometimes I identify it with S, and that's because I am working with c equal 1, and sometimes I'm not. If I want to be very precise and use general units in which c is different from 1, I have to distinguish between this S and tau. The coefficient should be c if I want this tau to be measured in time units. Otherwise they are exactly the same thing, and sometimes I just don't distinguish very much between S and tau. Okay, now since this S is a real number that in principle will be growing when if we keep x1 fixed and we get x2 runs along the curve, this gives you the idea that you could use S itself to parameterize as a parameter of the curve instead of lambda. So you could write that this delta S between the 2 points, okay, is the integral between the S, now I am using S as a parameter, okay, of the mu nu, the x mu with respect to S, the x nu with respect to S. Now it's obvious that this integral gives you delta S if this is equal to 1 or minus 1. Okay, so this implies that the property that defines the proper time, or is that this is equal to either plus 1 if the curve is time-like, or minus 1 if it is space-like. This is a very convenient parameterization, and we also remember that we discussed that this proper time would be the time measured by an observer that is commoving with the particle. Okay, so now that we have defined this functional that gives us the proper distance, we can define a geodesic as the curve that has a smaller length. In general, it is smaller. Sometimes it's the largest length, but let's say, suppose that it is smaller, and that well, so we can just search for extrema of this function. Now, so this is similar. Well, it is the principle of least action. If we call this functional an action, and we know that the x mu's of lambda that will have that property are those which satisfy the Euler-Lagrange equations of motion. Then in this context, those Euler-Lagrange equations of motion will be the geodesic equations, just as we had some autoparallel equations of the autoparallel curve. We have the equations of the geodesic curve, or just geodesic equations. Let us try to find these equations by varying directly the action or this function, okay, and imposing that the first variation vanishes. We have done this many times, so it's just an exercise. Okay, since lambda does not change, because these variations are variations in the curve, we are considering different curves that join the two points, initial and final. So it is x mu of lambda that changes, but not lambda itself. Okay, and we just have to consider the variation of the square root, and this will be 1 over 2 times this square root, and then the variation of what we have inside, x dot mu, x dot mu. These are derivatives with respect to lambda. Now, well, the first terms are just the same, and we have the variation of g mu nu first, plus g mu nu, the variation of x dot mu and x dot nu, plus, if you want, x dot mu, the variation of x dot nu. Now, since this is symmetric, I can, this is always symmetrized, but then I can interchange mu and nu, and I get, for instance, this term with a factor of 2. Okay, so let me write it. Okay, so this is, we have finished the first step of the variation. Now we have to consider that we are varying x's, and the dependence of the metric on x's is through the derivative. So this would be, it's just a chain rule. So this is delta x rho x dot mu s dot nu, plus, and here, okay, this is delta d lambda x mu. Since the delta does not involve changes of lambda, this derivative and the variation commute. Okay, and we have 2 times g mu nu d lambda delta x mu x dot mu. Okay, next step will be to integrate by parts this term, and remember that it is multiplied by 1 over 2 square root of all those things. And so because the idea is that we want to find the term which is proportional to delta x mu alone. Okay, so this first term is just 1 over 2 times the square root of g partial rho g mu nu delta x rho x dot new x dot new, and then there is a term which is a total derivative, and this term has 2g mu nu everything, in fact delta x mu x dot nu divided by 2 times this square root, okay, minus the lambda and the derivative of everything except for delta x mu, so it is g mu nu times x dot nu divided by this square root. If I have cancelled the factors of 2 and just delta x mu. Okay, the boundary conditions that we impose always will be that delta x mu vanishes on the boundary because the boundaries are fixed. All the curves that we are considering start and end at the same 2 points. So when we apply, when we integrate this term and we evaluate it at lambda 1 and lambda 2, this term will vanish with the boundary conditions. And we are left with these 2 terms, and if we want to rewrite them in with delta x mu as a common factor, I have to redefine to relabel tensor. So instead of rho, I'm going to write mu, and instead of mu I will write rho. X dot rho. So I can take delta x mu as a common factor, x dot rho x dot nu minus the lambda g mu nu x dot nu over this square root, and everything multiplied by x by delta x mu. And this means that this is just delta s delta x mu, and this is the first variation, and it has to vanish if the x mu extremizes the distance, the proper length between the points 1 and 2. Okay, we have still to message this expression here. We can do it this way. So let me write it. Let me write the equation. This will be the geodesic equation. Okay, it's just that we have to operate a bit to rewrite it in a more recognizable form. X dot nu divided by this square root equal to 0. This is delta s delta x mu. These are just the Euler-Lagrange equations. Okay, so now let's start operating. There is not much to do here in this term, but here we have to take the derivative with respect to lambda. So first we take the derivative of g mu nu, and g mu nu depends on lambda through x of lambda. So we use the chain rule. So this could be the derivative with respect to x rho of g mu nu, and then the derivative of x rho with respect to lambda, which is x dot rho. Then we had x dot nu and the square root, and the other term that we have, sorry, with a minus. Let me put it in this form. It's just the derivative with respect to lambda of x dot new divided by this square root, and this equal to 0. Well, we have x dot row, x dot new, x dot row, x dot new. So we are going to take them as common factors, x dot row, x dot new, and we also have this square root, and then we take also this factor of 2. Okay, so what is left here is partial mu g row new minus 2 times partial row g mu new. Now observe that this expression is symmetric in row and nu, which means that, okay, maybe I write this in this order because it's just easier to symmetrize these two things. They are automatically symmetric. And if I expand this symmetrization to make it explicit, so remember that this has a factor of 1/2, this means that I have the row g new mu minus the new g row mu minus g mu new the lambda x dot new over this square root equal to 0. Okay, we are almost there, because now that you have 3 terms with derivatives of the metric with different indices and all but one with the same sign, this should remind you of the Christoffel symbols. In order to make this more explicit, we are going to multiply the whole equation by the inverse metric, so say j mu alpha. So here, multiplying by this, we will get delta nu alpha, and in the end the only thing that happens is that this term, this index, changes from nu to alpha. And I'm also going to multiply all this by a minus sign. So doing this, I get x dot alpha divided by this square root, and okay, I reverse all these signs and I change the order of these terms. So I write this first, and they come with a plus, so it's alpha mu, and then I have the row g nu mu plus the nu g row mu minus the mu g row nu. Sorry, and this comes with a plus. Oh damn, okay, the lambda x dot alpha divided by this square root plus 1/2 and this square root, and this is equal to 0. Now this is nice because this is these are the Christoffel symbols. Alpha is the free index because we have sum over mu. Now you see that this expression is symmetric in row and nu, so we can write it like this. And there is x dot row x dot new equal to 0. Okay, we're almost there. So we get the lambda x dot alpha plus 1 over this square root. And okay, I write the Christoffel symbols. I could say that I am writing the Levi-Civita connection, x dot row x dot new equal to 0. Okay, you could divide the whole thing by 1 square root of g x dot, just to write everywhere this in this form. Okay, this is a question of aesthetics, because then you have x dot divided by this square root everywhere. But you can also do something else, and okay, this is the geodesic equation. In terms of an arbitrary parameterization. Okay, we put it in a box. Okay, just by construction, this equation always has the same form for any parameter, and if you change coordinates, it will also have the same form. Okay, g mu will change form. The Christoffel symbols will take a different expression. The coordinates will be different, but the general form of the equation is always the same. Now, if we use the proper length or time, okay, which means that this square root takes the value 1, because what is inside takes the value also 1, because we take the absolute value of g mu nu x dot mu x dot nu. In that case, this equation takes the form x double dot alpha plus rho nu alpha x dot rho x dot nu equals 0, which is the same equation as the autoparallel equation, but with the connection being given only by the Christoffel symbol, or the Levi-Civita connection. So if the connection in the autoparallel equation is the Levi-Civita connection, well, it's the same. And we write it in terms of the affine parameter. This equation is the same as the geodesic equation given in terms of the proper length. So here the affine parameter is equal to the proper length with the Levi-Civita connection. And we see that, well, geodesics and autoparallel curves are the same thing if we use the Levi-Civita connection. The only thing that may worry you is that we have only found that these equations are identical when we use the affine parameter and the proper length. But what happens if we use any other parameter? Because we had an autoparallel equation for arbitrary parameters. Okay, so we just have to operate a bit. Okay, we take this equation, we multiply by this square root squared, just to remove all the square roots. So we get something like this: the lambda x dot alpha divided by, oh my god, this square root plus rho nu alpha x dot rho x dot alpha equal to 0. And now we take the derivative. So this gives x double dot alpha plus square root the lambda 1 over the square root plus this term that I don't bother to write explicitly, and this times x dot alpha. This is d minus the lambda of the log of the square root. Okay, because this is a function of lambda when we substitute x mu of lambda times x dot alpha, and in the end we arrive to this form: rho nu alpha x dot rho x dot nu equal to the lambda log this square root x dot alpha. Now you compare this with the autoparallel equation. What you find is that this should be identified with the proportionality coefficient f. So the geodesic equation also for any other parameter is equivalent to the autoparallel equation when the connection is the Levi-Civita connection. And here it is very easy to see that if we use the proper length, since this square root will be equal to 1, it's constant, the logarithm will be 0 and the derivative will be 0 and the right hand side will vanish automatically. Okay, now we need to go back to the physical interpretation of this and to relate it to some other things that we saw in the past. So remember that x mu of lambda gives you the world line. Now x dot mu of s, so I take the derivative with respect to the proper length or proper time, in fact, because this will refer to time like curves, is the proper velocity of the particle. We use any other parameter, the value of the velocity will be different. It will be parallel to the proper velocity because there is just a factor ds over d lambda, but the value will be different. And how about the proper acceleration? The proper acceleration in Minkowski spacetime was just the second derivative, but the second derivative we have discussed many times. It is not, it doesn't transform as a tensor. This is a vector. Okay, in fact, a contravariant vector, but this is not a vector. What is a vector is this whole thing here. Okay, but we have written in many different ways. So this is a vector, rho nu alpha x dot rho x dot nu, and this thing is we can write it like this, and this is the proper acceleration. Okay, so these are the three physical concepts that we find, and the conclusion is that along a geodesics are curves along which the proper acceleration vanishes. Now we will make exercise about all this and in the context of gravitational fields. So don't worry, now we are collecting a lot of concepts that will be put to use soon. Okay, there is a trick that people use to write this equation, because if we want to find geodesics, we need to write first the equations, the geodesic equation, and then we need to solve it to find solutions that satisfy that this proper acceleration is equal to 0. There is a shortcut to find this equation, which would be to consider this action. Where here x dot mu is the derivative of x mu with respect to s. Okay. Well, it is not a reparametrization invariant or anything, but the main virtue that, as we explained in this moment, is that if you vary this equation, you find equivalent equations. But you have to be very careful, okay? Because when you when you vary this, you're going to get equivalent equations, and sometimes this is used not just to get the geodesic equations, but also to compute the Christoffel symbols, because they are given there. You just look for the terms which are quadratic in derivatives, in first derivatives of x, and those coefficients will be the Christoffel symbols. But you have to be very careful, but because the equations that you get by varying this action are really these ones, okay? So if you search for the coefficients of these first derivatives, the coefficients will not be the Christoffel symbols or the Levi-Civita or the components of the Levi-Civita connection. They will be those, but multiplied by the metric. So to get g mu nu gamma alpha beta nu. So be very careful with that. If you use it correctly, there is no problem. When the metric is diagonal, it is very easy to invert, but when the metric is not diagonal, this multiplying this by the inverse metric can be tricky. In any case, you will have to invert the metric if you want to compute the Christoffel symbols, because remember that the Christoffel symbols have an inverse metric multiplied by 3 terms. Okay, here it is the inverse metric. If we compare the equation of the geodesic with the equation of motion of a freely falling particle in a gravitational field that we derived in lecture 2 when we studied the principle of equivalence, we will arrive to the conclusion that most likely, and this is something that we will have to check or test later, freely falling particles follow geodesics. The world lines of freely falling particles are geodesics. We know that if we fall with many other material objects, we will not observe any gravitational effect in a small neighborhood of where we are, okay, which would be our origin of coordinates. However, if we look to a wider neighborhood, we will start observing tidal effects, which are manifestations of the existence of a gravitational field there. These tidal effects, for instance, are the most typical tidal effect would be the convergence of the world lines of freely falling particles in the Earth. Okay, we see that they converge to the center of the Earth. So if I fall with more objects, I will see that they just approach slowly. I can only see this if I spend enough time falling, okay, which means that my neighborhood in space-time, at least in time, is large or not small, or if I consider objects that fall really at spatial distance, and then this effect of convergence to the center of the Earth will be more visible. So these tidal effects in general become manifest when we examine what happens in a neighborhood which is not small. Okay. Now we want to characterize this convergence, produced by a tidal effect, and in a more rigorous way, and we are going to consider the following setup. We consider a set of curves which will be geodesics, so each of them represents the motion of a material particle. Okay, and I'm only drawing just a few because they are supposed to be an infinite number, so through each point there is geodesic. Okay, so instead of writing just one equation x mu of psi will be the evolution parameter for one of them, the other, and the other. Clearly, it is much better and should be possible to write all of them by adding a second parameter. So for instance, for sigma 1, I get this curve, and this curve could be x mu of psi sigma 1. For x sigma 2, I could get another curve, psi sigma 2, and so on. Okay, sigma is a continuous parameter, so I get really a continuous of geodesics. But I can also fix the parameter psi, the evolution parameter, and I can say that if it at a fixed value of this evolution parameter psi 1, I get a curve which will be transverse, okay, and which will cross the rest of all the geodesics, and at the point sigma 1, sigma 2, and so on. This will be given by x mu of psi 1 sigma. For another value psi 2, I will get something slightly different, x mu psi 2 of sigma. So this is the setup, And we can imagine that this represents the motion of an infinite number of particles which are freely falling in some gravitational field. In this setup, I can define the vector tangent to all the geodesics. Now it is a partial derivative because x mu depends on psi and sigma, and it is the partial derivative with respect to the evolution parameter psi. For different values of sigma, this gives me the tangent vectors to different geodesics, and for different values of psi, I get the tangents at different points of each of the geodesics. But I can also define an epsilon mu, which is the partial derivative with respect to sigma, which labels the geodesics. Okay, and if the v mu's are this, okay, then epsilons are like this. Okay, for different values of sigma and psi. Now this epsilon mu gives me information about the separation of nearby geodesics, because after all this is just it's a limit when some increment of sigma goes to 0 of the geodesic which is placed at sigma plus delta sigma minus the geodesic at sigma divided by delta sigma. So this gives me information about the separation of the geodesics, infinitesimal, of course. Well, what I want to measure is how this distance between nearby geodesics increases or decreases, because it will represent, if they increase, that this geodesic separate, and if they diverge, if they this distance decreases, the geodesics converge. And so it looks like I should look at the derivative with respect to psi. Now I will see how to define this more precisely. I want to see how this epsilon mu changes when psi varies. So I would like to study the derivative of epsilon mu with respect to psi. I will define this better. However, this simple measure of convergence of divergence is not enough to characterize the presence of a gravitational field and to characterize tidal effects, because in flat space-time, in absence of gravitational forces, it's clear that I can have motion which is convergent. I just need to choose appropriately the initial conditions, and the motion of all these particles will converge, and I have infinite number of trajectories that converge to a point. However, if these are freely falling particles in absence of gravity, so they are moving in Minkowski, the rates at which these trajectories approach, or these whirl lines, will be constant. Then the first derivative would be constant, and clearly a better representation of tidal effects would be the second derivative, which will be 0, because we know that in this situation there are no tidal effects. Okay, now I'm going to define a bit better this rate of convergence. We have to take into account that epsilon mu is a vector, so we have to act on it with the covariant derivative. Otherwise, the result that we will obtain would not be invariant under changes of coordinates. And in order to take derivatives with respect to psi, what we do is to project the covariant derivative with the tangent vector. Okay, so this is the quantity that we want to compute. Okay, remember that because this is this derivative, okay, we may denote this derivative this way, because really we are taking the covariant derivative in the direction of v, which is the direction in which psi changes. This would be the rate of deviation that we said that in the flat space-time case, in absence of gravity, is a constant. So what we want to compute, okay, this is sometimes this can be represented like this, or also like this. Okay, you want this is a different notation. What we want to compute is this quantity, which is the geodesic deviation. Okay, this is the definition. And the geodesic deviation equation relates this quantity to the curvature. Okay, so we just have to start computing this quantity using the properties that we know. Okay, this is this sequence of operators acting on epsilon mu, and we are going to make use of this property. Okay. It's a property parties notation. So if we take the derivative, covariant derivative in the direction of v of epsilon mu, okay, this is this by definition, and now let me add and subtract some quantity. This quantity will be epsilon mu v mu plus epsilon mu v mu. There is a name for this combination, this particular combination, which is the D bracket, and it's represented like this. It's an operation which is bilinear in two vectors and which gives another vector. This is certainly another vector. Okay, so using this representation here, I can write now la v of v epsilon plus epsilon mu, well, just to make this coincide with the nodes, I will write it like this. Okay, so let me remove this. And okay, now we want to compute this quantity. And the main property that this D bracket has is that it's really independent of the connection. This is something that we are going to check explicitly. So we define this in this way. If I now use explicitly the form of the covariant derivative, I have this minus epsilon partial nu v mu plus gamma nu rho mu epsilon. Sorry, this should be v rho. Okay, so this is v nu partial nu epsilon mu minus epsilon nu partial nu v mu plus, and I have nu rho mu v nu epsilon rho minus v rho epsilon mu. This is just the antisymmetrizer with a factor of 2. Okay, and this means that this must be antisymmetrized because it is contracted with it. But if we are using the Levi-Civita connection, as we are, okay, then the antisymmetric part is 0, and this is just not there. This means that really this D bracket can be defined only in terms of the partial derivatives, and although it looks a bit surprising, the result of this is really a vector, although we are using only partial derivatives. Okay, as you might suspect, this Lie bracket is related to the Lie derivative, which is one of the derivatives which we said transforms tensors into tensors, and which are different from the standard covariant derivative. And it is different because it does not involve the connection. So let us compute this. Okay, according to the definition of this, this is nu, partial nu, epsilon mu minus x nu partial sigma in nu v mu. Okay, so if we use the chain rule, we see that really we are taking the derivative with respect to psi of epsilon mu minus the derivative with respect to sigma of v mu. But this is the derivative with respect to sigma of x mu, and this is the derivative with respect to psi of x mu. Since the partial derivatives commute, then this is identically 0. So this Lie bracket gives me 0. Then we have to compute what is left here. Oops, and I realized that I have made a mistake here, and instead of psi, this should be epsilon. Okay, now I proceed as before. I add and subtract a term, and which one we see now. The idea is that if I have antisymmetrized derivatives, the curvature will appear at some point. Okay, so this is why I add and subtract. Let me rewrite these first two terms as this commutator of covariant derivatives in the directions v and epsilon. And then the last term is this derivative. Okay, before I go on, you just have to see that so far I have not used the fact that the curves x mu of psi are geodesics for all sigma. If they are geodesics, then the tangent vector is autoparallel and satisfies this equation. Okay, but this is just nabla v nu equal to 0. Okay, so this term will vanish the moment I impose that all curves are geodesics. I will not do it for the moment, okay, but I can obtain a general formula for any kind of curves, and then we can specialize it for the particular case that these curves are geodesics. Now I want to compute this commutator. And I just expand the definition of this. So this would be v nu acting on nabla epsilon v nu, which is epsilon rho nabla rho v mu, and the term in which I interchange epsilon and v, which I can write in this way. Okay, now I operate. I'm using Leibniz rules. We have epsilon rho, nabla nu, nabla rho v mu. And then from the second term, I get minus epsilon nu, nabla nu v rho, nabla rho v mu, minus epsilon nu v rho, nabla nu, nabla rho v mu. These two terms here are proportional to nabla rho v mu. I can take a common factor, and they are just this times nabla rho v mu, and we recognize the Lie bracket of epsilon and v, which we computed before and which is 0. Okay, So this term just vanishes. And the last two terms, the terms that remain here, are proportional to nabla v, nabla rho v mu, that I also can take as a common factor. So I write v nu epsilon rho minus epsilon nu v rho times nabla nu, nabla rho v mu. But this is nothing but 2 times epsilon, v nu epsilon rho antisymmetrized. Remember that this antisymmetrization carries a factor, normalization factor of 1/2 times nabla nu nabla rho v mu. But because this is antisymmetrized in v nu, these two derivatives are antisymmetrized. The indices are antisymmetrized in v and rho. Okay, then if I have two covariant derivatives, the product of two covariant derivatives antisymmetrized this way. Okay, this is this, but with 1/2, because I have the factor of 2 here, this is just the commutator of the two covariant derivatives. And I can use the Ricci identity for the Levi-Civita connection. I can also remove these antisymmetrizers here because they are unnecessary. Well, now the commutator is clearly disymmetric in nu and rho, so this is an unnecessary antisymmetrizer because this is automatically antisymmetric in nu and rho. So I just remove it to simplify the expression, and here we get R nu rho sigma mu V sigma. And if you want, we can now collect the whole the result, and this would be epsilon mu equal to V nu epsilon rho V sigma R nu rho sigma mu plus nabla epsilon nabla v mu. This is the term that we had not computed yet here. Okay, when we are talking about geodesics, this term is not there for geodesics. And then this is the geodesic deviation equation. The result is exactly as we advanced. This geodesic deviation, which is a manifestation of tidal forces, is directly related to the curvature, which somehow measures gravity in a way in which the connection cannot measure because of the problems of the connection, which is not a tensor. If you want to remember this equation, well, first of all, you have to know what the geodesic deviation is. So you have to know this definition. It's just two covariant derivatives with respect to v. Although we have denoted it in this way, so it is understandable that the right-hand side has two v's. Okay, the left-hand side also has one epsilon, so there must be some one epsilon on the other side. An upper index mu free, so there must be an upper index mu here. And now how I contract these three vectors with the curvature. There are not so many ways to do it because in general, if you do it in the wrong way, you get automatically 0. Because this the curvature tensor, the Riemann tensor, in this case, because we are using the Levi-Civita connection, is antisymmetric in nu and rho. So if we contract two v's with the first two terms, we will get 0. So it has to be a v and an epsilon. Now the order, you have to make the computation in order to find it, okay, which is equivalent to fixing the sign here, which is these conventions and so on, and writing this expression just in this way. But up to this sign, or if you want some numerical coefficient here, you can determine the structure of this term just by inspection, okay? And you should remember this formula. So what are the uses of this formula, apart that it confirms what we had understood conceptually, that tidal forces are they manifest themselves in geodesic deviation, this convergence or divergence of geodesics filling some part of the space-time. So the space-time you can consider is full of these geodesics. There is one geodesic going through each point. This is called technically a congruence of geodesics, okay, but I didn't want to introduce this word. Apart from this, from understanding this that we had already imagined, this formula is crucial to understand what is the effect of a gravitational wave. It is gravity, so if there is gravity, there will be curvature, and well, the effect on a set of freely falling particles. This is where you study how to detect the gravitational waves. Basically, you study the effect on freely falling particles. In this way, you discard whatever inertial accelerations that may happen, and all that you detect are the tidal forces, which are if you want, some people think it is the most genuine manifestation of gravity, which will be produced by the gravitational waves. So when we study the detection of gravitational waves, we will go back to this equation. We will imagine a set of freely falling particles, and they will follow geodesics, and we can apply to those geodesics this formula. And the whole thing will be to study the result of that calculation will be to study how this epsilon fluctuates when the curvature tensor corresponds to a passing gravitational wave.